Okay, so the default method I want you guys to use when you're writing the electronic configuration of an element is to use the periodic table. Okay, so remember we labeled the periods 1 through 7. Okay, so you can just count across, like if you're in period 1, you start off in the S block, right? There's a reason they put the names. Okay, so this is first two in here is going to be S. Okay, and then as you move across to the right hand side, this is P, okay? I guess I should put letters in there. So all these will be S's, all these will be P's. Come here. Anything here will be your D's in the D block. And the F block isn't shown on here, but anything down in yon F block, which would be down here somewhere, as we know, would have an F designation. Okay, so you can just read right across. So for this particular element here, we can just read across. So 1s2, 2s2, 2p, 1, 2, 3, 4, 5, 6, 3s2, 3p1. Okay. As you can imagine, as you get further down the periodic table, that gets a little bit cumbersome, right? Because if you were doing like the electronic configuration for xenon or something, just think about all those like subshells you'll have to write out. So we do a thing which is called condensed electronic configuration, which kind of cuts out the boring bits, if you like, because if this mystery element was going to be undergoing chemical reactions, the only thing that matters is the outer electrons, aka the valence electrons, okay? So these guys down here, let me get something to draw with. This is what we call the core electrons, and these are the valence electrons. So the core electrons are not involved in chemical reactions. So really, do we need to keep listing them out every time we write the electronic configuration? So what we do is we use a shortcut, which is a condensed electron configuration. So you look at the end of the period above where your element is, and the noble gas at the end of that period can represent that whole core. So if you were to write out the electronic configuration for neon, it'd be 1s2, 2s2, 2p6. So we can do a shorthand. Instead of writing 1s2, 2s2, 2p6, we can just write neon, and we use square brackets to show that that's the core electrons, and then 3s2, 3p1, okay? So I'm going to do a couple of others because these are kind of, once you get to know what you're doing, they're very, very quick, right? So let's just pick any other element, right? And like I say, you don't have to know what the element is. It's just showing us based on position in the periodic table. Okay, well, this is kind of boring. Okay, so for this one, go to the end of the row above. It's helium. So the core configuration, if you can't be asked to write out 1s2, it's just going to be helium, and then 2s2 will take us to where that highlighted atom is. Okay, so I guess that one didn't save us much space and effort there, but you know, them's the breaks. All right, let's do another one then, because that was literally the most silly example we could have had. Okay, this is a great one. So here we have something which is post the transition element, so we're going to have to include our d electrons in there as well. Okay, so you could write 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, because they're filled, then 4p1, 2. Okay, obviously that is a bit of a mouthful. So you would just use the core configuration of the noble gas at the end of the row above, which is argon. And that takes care of those first 18 electrons for you. So as you can see, as you go further down the periodic table, it gets more and more useful to use this condensed electronic configuration. Then read across the period that your element is in. 4s2 fills first, then 3d10 fills, and then 4p count across to the element that we care about, 1, 2. So there's 2 electrons in the 4p orbital, okay? That will seriously save you time, and it's pretty much foolproof, okay? So from now on, always do it that way.